So hello everybody, welcome back. And this is session number 5. And the topic for this session is ethical considerations and social media analysis. Right now we have a paper that's called Personality Profiling. How informative are social media profiles in predicting personal information? And we have Louis over here. This is a short paper with 50 minutes.
Thank you. Thanks for rushing back from lunch to be here. So it's great to be here because I am not a language technologist by training. I'm a math guy. I study social media, social networks, online influence, things like that. So I've certainly used NLP for many years. Have to tweak things, have to understand these models to a certain extent, but not deeply in the field. And so it's been really fantastic to come along to this conference and learn about what people are doing and what the state of the art is in this field. So I mentioned that to say that nothing that I'm going to talk about here today is going to be incredibly high tech. And that's because we come at this very much from the sort of data science, statistical data science, like understand your data, know your data, sort of a viewpoint on these problems. So yeah, this is hopefully this will still be interesting and can still learn some things from looking at the data and the ways that we attack it. And then the next thing to say is that I'm the third author on this paper, and this is not really my work. I'm here at this conference standing on the shoulders of others, standing on the shoulders of giants. So Josh Watt, the lead author on this paper, this is really his work from his master's thesis. So a master's by research thesis from a couple of years ago now. So let's meet Josh. So he was a master's, an MPhil student, so it's like a little bit of coursework and then a chunky thesis. MPhil student with myself and John O'Tuke, the second author, in 2021-22, submitted early last year. And so this was part of his, this study was part of his project. He also worked on social media analysis of a particular misinformation campaign during the early days of the war in Ukraine on Twitter. So yeah, he's unfortunately for us, we didn't manage to lure him into a PhD because he got a sweet job in this defense contractor in a defense company in Adelaide called Consunet, not Consent. I got auto corrected there, where he's an applied scientist. So for the DSTGers in the room, you might know about Consunet, and Josh Watt is hopefully going to be helping us on some projects that we're going to be doing with DSTG pretty soon. So yeah, so he looks like a footy player because he is. If you follow him on Instagram, you see some very amusing videos of him DJing all around the world, which I think is a great scam that he runs to get free drinks all over the place, which is brilliant. But he's also this incredibly clever human, so it was a really great pleasure to work with him. And I linger on this slide so that you can see Josh Watt, and it's really all the credit is to him for this cool stuff. So what's this all about? So Josh came to us wanting to do a master's, and he was really fascinated by Cambridge Analytica, basically. And so he was really fascinated by that idea of psychological profiling from social media data, what you can learn about people from their digital traces, and things like how Cambridge Analytica purported to do micro-targeting. So the concept for the project, I pitched it yesterday as Cambridge Analytica, but for Twitter, and with a different personality model. That's a little bit of an oversell. The pitch for the project was basically, well, let's try and figure out how much of that sort of science is basically bunk, right? Like, let's see if we can pen test that. So, how did Cambridge Analytica work? Well, they use this very famous psychological personality profiling model called the Ocean model, which you may have probably heard of, the big 5 personality traits: so openness, conscientiousness, extroversion, agreeableness, and neuroticism. And they could find, they had people basically take a personality test online, and then they mine their social media mine their Facebook profiles, and built a model to predict personality type based on things like likes and stuff like this in your friendship network and stuff like that. So really creepy. We didn't do the ocean model because the really key thing about it, the real evil genius of it, was they paid people like a couple of bucks to sit an online personality test, so they could do that personality test and so they could get these psychological characteristics, and that was sort of the response variable that you then build your predictive models out of. So we didn't do that. So the first substitution that we made was, well, we didn't have access to Facebook data. We did have access to Twitter data at the time, and not so much on the ocean model. But Josh found a clever way of getting information about people's Myers-Briggs personality type. So this is a different type of psychological model. I should say right up front, psychologists don't like this at all. They cringe whenever we talk about this model because it's not well regarded. It basically comes, like Freudian, basically, and psychologists don't like that ever before. So take everything with a big grain of salt that I'm about to talk about here. But Myers-Briggs is still definitely used in for personality testing when you go for job interviews and things like this. So it's still out there. It's still being used, and you've probably heard of it. It basically splits personality into these 4 different areas, and there are these 4 different dichotomies. So you are either introverted or extroverted, you're either intuitive or sensory, you're either thinking or feeling, and you're either judging or perceiving. And there's language and words that go around each of these. And so you pick one thing from each of those bubbles, and you get there's like 16 different personalities that you can be. So you'd be like an INTJ or something like this would be your personality type, right? So you can do these tests on a website, see what personality type you are. You've probably might have been done it if you've gone for a job. And then, the theory is that you can use that to assign people into teams and things like this. So, okay. So, I'll get to in a sec how we establish these personality types. But quickly, what have people done with this before? I mean, heaps of people have studied Myers-Briggs, but specific social media stuff. So, the first thing is, what are the proportions of these personality types in the general population? There are reports of that from the Myers-Briggs, from the company that does that testing now. So they report this for the general population. I'll show you, we'll use that in a sec. There have been some social media studies on this as well. So a survey study done in 2012, surveyed a bunch of people about personality types, and then 1,748 people of however large that survey was reported that they have a Twitter account, and then they track they recorded the personality types for all of the people in the study. So there's some data on personality types of people who responded to this survey who have Twitter accounts. And then the closest thing to what we did is a paper from 2015 by Plank and Hovey, where they actually built a classifier based on some self-reported personality data that they have for a small data set of like 1,500 Twitter users. So, okay, so what did we do? The state of the art here in terms of data is like basically that 1,500 Twitter users. So the first challenge with this is how do you get data on this? So here's the brilliant thing that Josh realized is that people do these personality tests online, and then they go to Twitter and they self-report. I am a 4-letter acronym. So I am an INTJ or I am an ES, something. And so he basically said, oh, well, I can just search for this. So I can write 16 different search queries on the Twitter API. And so I can search for when people put these characteristics in their profile information, or when they put in their tweets, I am a such and such, or I am this, or I am that personality type. And so he basically searched for this using the full archive search at the time, and came up with 68,000, 69,000 users. Did some checking of those. A few of those were mislabeled as people are saying, I am not an X, or I don't think I am an INTJ or something like that. So a little bit of mislabeling. We did some filtering on this data. Josh did some filtering, but ended up with 43,000 users and their full tweet history where they've self-reported this personality type. So great, brilliant idea. We've already got a huge data set to play with. So what do we do with this? Basically tried to be Cambridge Analytica. So grabbed all of the social network, the social metadata that you can grab. So, number of followers, number of friends, things like this. Did a bunch of, we have all the text as well. So you can do a bunch of standard NLP. So we did Luke, sentiment type stuff on this. There's one, I guess I lied. There's not all traditional stuff. There's a BERT in here. So there's one transformer in this. We did BERT word embeddings of people's text, and then we did some checking for bots as well. So they're the type of features that we used. So looking at the data, so here are the 4 different dichotomies: extroverted versus introverts. Our data set, if we just maybe look at the extroverts versus introverts on the left there. So our data set's on the left, so the proportion of extroverts versus introverts in the data set. Twitter is the, I believe is that survey study of the 1,700 users, the proportions of those, and then general population is what Myers-Briggs report on their own website. So you can see that Twitter's non-representative, right? It's more introverted than the general population. Via this, very biased, strange self-reported sampling that we did. Caveat to everything here. Not so bad for this judging versus perceiving things, and etc. Okay, so we did a bunch of things. 2 minutes, that's fine. We did some upsampling. We did a few standard machine learning methods. We upsampled and downsampled to address class imbalance. Found that we didn't actually, we got the best performance on these models if we didn't do anything, surprisingly. And, there wasn't a huge amount of correlation between the personality type. So I could basically build independent classifiers for every separate dichotomy, for every separate personality type. And that sort of worked okay. So let's see. So comparing with this Planck and Hovey model, so in the top table here, it's kind of a wash. They do better on some of these on 2 of these dichotomies. We do better on 2 of the others. I would say that this is a hard problem. You actually, accuracy is, a funny thing here. As you get down to the table at the bottom, we're looking at the predicting, 1 of the 4 dichotomies correctly, 2 of the dichotomies correctly. So by the time you get up to predicting all of the 4 dichotomies, baseline on that is 1/16, 100/16%. So there are low numbers there, but they're actually sort of not so bad when you consider that it's not a binary classification problem anymore. Okay, that's, the model works okay. Let's talk about some of the fun stuff. You can do variable importance plots here to look at what are the most predictive features for introverts versus extroverts. So sadly, you can't see it, but having geo-enabled tweets is the most predictive feature for being extroverted, as you might expect. Feelers versus thinkers have, high sentiment in their profile. So there's all this. Oh, stop! But I want to show you the picture of the emojis here. I'll linger on this. Do the same thing just for like the use of emojis in tweets, and you can predict sentiment from emojis. So being a feeling type person, the most predictive emojis of that are the sad face and the love heart and things. So there's all these funny things that pop up and kind of make sense actually. So I'll stop there. This is all representative, but maybe the last comment that I'll make is that Myers-Briggs actually popped up in the first keynote yesterday in a discussion of how it's important, if we're going to understand the personalities of LLMs, we need to understand the underlying data. So this is kind of just a fun study, but I think the idea of understanding the personality of social media data, of people's social media data, is important because it's the basis for understanding the personality types of these large language models, which we all care about. So I'll stop there. Thank you very much.
Yeah, thanks, Lewis. This is great. Really interesting talk. One question is, are you aware of the hexacode model?
Hexacode.
Yeah, so it's another personality test, but that also, it can look into the dark triad, narcissism, Machiavellism, and psychopathy.
Ah.
And I'm wondering whether that, you could look at the converse of that, use this to say, can you predict behavior which is, not so nice?
Let's talk afterwards.
Yeah, okay.
The question is, how you get data that you can do supervised training on or something.
Yeah.
But yeah, let's talk more. That sounds cool.
So you mentioned it's a biased sample, but you did things to try to adjust for that. But then on that plot showing the different distributions, the bias seemed to be that you had more introverts and fewer extroverts, which is the opposite of what I would have anticipated. You think it's the extroverts who are opposed. So what's going on? Any idea?
Don't know is the answer. We did wonder about that. A theory here might be that social media is a safe space, in the real world, in the physical world. If you're introverted, where does your community become there? Maybe it becomes online. So maybe there's some overrepresentativeness of people, interacting in the safe space. It kind of seems funny and quaint to call Twitter a safe space for introverts, but interact on today. But yeah, there's a theory about that, but we don't know.
Well, and if I may, a follow-up question. I'm curious, you've now got this classifier. One thing you could do is take someone's tweets, classify it, and see if it disagrees very confidently with what they say. Because you can imagine people are changing, not answering truthfully. So did you try that? Did you find cases
Well,
where
I mean, that's what these accuracies and things are talking about here. So, taking out a sample of the data. As for changes over time, that's a really interesting question. And yeah, you could, we didn't look at the evolution of these personality types over time.
So sorry, I should have clarified. What I was thinking is, imagine I did a personality test, didn't like the results, and then lied on Twitter.
Oh.
You could run your tool, find a person where it's really confident that it's that, which is not the same. And for the really confident, you could look at them and say, well,
Oh, right. Yeah. Okay. I'll look at the people who disagree. No, that's a great idea though. So actually look at the sort of misclassifications here, or the people who disagree. Yeah, cool. That'll be the next student who wants to do this stuff. Cool. Thank you.
This one is online. Okay. Yep. We're gonna start. All right. So the next paper is Truth in the Noise, unveiling authentic dementia self-disclosure statements in social media with large language models. The presenter is Daniel, and this is a short paper. Daniel, whenever you're ready.
Yes, thank you very much. So hello, good afternoon. My name is Daniel Cabrera Lozoya. Unfortunately, I was unable to be there in person to discuss our research. So I truly appreciate the opportunity to present our work remotely. Today, I'll be presenting on behalf of my peers, Dr. Yud Michael Yun Leng, Dr. Laura Hemi, and Dr. Mike Conway. Here is a quick overview of the points that I'll be discussing today. So to start, I would like to provide some context and talk about the motivation behind our work. So there are multiple longitudinal studies that have linked linguistic decline to dementia onset. While this type of research offers very valuable insights, it is often challenging and costly to collect this amount of data. Recently, social media data has become a promising source for creating cohorts for longitudinal studies, as data that's collected in this way can be continuously and passively collected from users' interaction. Additionally, one advantage of collecting user data via social media is that each of the posts are timestamped, meaning that it is quite easy to track changes over time. A key step in social media analysis after the data collection process is over is the data annotation process itself. Traditionally, regular expressions have been used to identify self-disclosed statements, such as I have COVID, I have lung cancer, or I have dementia, and so on. Now, while regular expressions are very straightforward to implement, they often prove a bit unreliable for conditions like dementia, since disclosures are frequently meant to be interpreted as jokes or are just sarcastic. An alternative that has been used in order to avoid using regular expressions has been to do the annotation manually, but this is very time-consuming. Hence, for our research, we aim to use large language models to identify authentic dementia self-disclosure tweets. Basically, what we wanted to do was to automate the process of annotating the data using large language models. But it is something important to remember is that the performance of large language models depends on the quality of the prompt that you use to instruct them, meaning that higher quality prompts tend to generate higher quality outputs. So we ended up developing a genetic algorithm to optimize prompts for large language models. The contributions of our research are the following ones. So first, the genetic algorithm itself. We also discovered some valuable insights of the performance of different state-of-the-art prompt engineering techniques for large language models. And lastly, we built a dataset of dementia tweets. To build that dataset, we used the Twitter Academic API to collect tweets that contain search terms such as I have dementia, I got dementia, I was diagnosed with dementia, and so on. We ended up collecting approximately 14,000 tweets that were annotated by each of the authors. And we ended up dividing them into a training and testing dataset. The distribution was an 80-20 split. Then the training dataset was then divided into 10 stratified batches. We ended up using that dataset to train our genetic algorithm. Here is an overview of the genetic algorithm we ended up developing. I'll be explaining each of its components step by step. So when describing a genetic algorithm, one of the key components to understand is what constitutes an individual within a population in the genetic algorithm. In our case, an individual is composed of 3 components. We have a mutation prompt, an instruction prompt, and finally, the fitness value of that individual. So the way that it works is that we have an instruction prompt that is going to be used to instruct the large language model on how to label a batch of tweets. The output of the large language model is then classified using a BERT classifier, which will predict a 1 for text that indicates that the user has dementia, and a 0 for users that do not have dementia. Now, these predictions are then used to calculate the accuracy of the instruction prompt. The accuracy in itself is the fitness value of the individual. Something that I would also like to highlight and mention is that the way that we ended up creating these instruction prompts was by using some mutation prompts. The mutation prompts that we used were based in 4 different mutation pools. Each of these pools are based on a state-of-the-art prompt engineering technique. Namely, we used chain of thought, expert prompting, generated knowledge, and self-critique. Here is an example on how we create a new instruction prompt for a new individual. So here's an example of a mutation step. So we have an instruction prompt, and we also have a mutation prompt here. This mutation prompt was selected from the generated knowledge mutation pool. And we ended up using these two instructions as inputs to a large language model that will then generate a mutated prompt, which will be the new instruction prompt for a new individual. Now that I have explained what is an individual and how they mutate, I will explain the evolutionary process in our genetic algorithm. The way it works is that our genetic algorithm will be run for n generations. And it starts with a base population of multiple individuals. So at each generational step, each individual has a probability of mutating. The mutated individuals are then incorporated as candidates to the population. Once the maximum population has been reached, then there is a process of selecting individuals with higher fitness. The way that we did our selection process is through a roulette wheel selection. The idea is that we normalize the fitness of all the individuals, then we use that normalized value as a probability function to select the survivors, meaning that individuals with higher fitness have higher chances of surviving. So that is the overview and how our genetic algorithm works. The experiment that we ended up running was using the following setup. We ran our algorithm for a total of 20 generations, setting a population limit of 10 individuals. And at each generational step, each individual has a 50% chance of mutating. And the large language model we ended up using was Llama 3. So in the left, here's the final prompt that was generated. So basically, after the algorithm ran for 20 generations, we selected the prompt that had the highest fitness. And we used this specific prompt to test its performance using the testing dataset. In order to compare the performance of the prompt we generated, we used a BERT classifier and a traditional regular expression approach as baselines to see how it performed against or in comparison with our own model. And the result is that our model outperformed both of these two approaches. Now, something that we also wanted to keep track was how each of the mutation pools performed. So in our experiment, something that we kept track was the performance of each of the mutation types. And we discovered that the self-critique prompt engineering technique was the most effective and the most common across multiple generations. But something interesting that we also observed was that the prompts that were surviving, or the prompts that had the higher fitness, integrated elements from various prompt engineering techniques. Meaning that we concluded that the optimal prompt engineering approach involves combining different prompt engineering techniques in order to mutate and evolve each of the instruction prompts. Now, we consider that there's still a lot of future work that can be done based on our research. One avenue would be to test and evaluate our genetic algorithm, but with different languages. So far, we have only tested it using the English language, but we consider that it is a very straightforward change that needs to be done to our genetic algorithm. It's namely just changing the language of the prompts that we're using. And we can test it in Japanese, German, French, Spanish, and many other languages. Another thing that we consider that can be discussed is to evaluate the performance, not only for identifying self-disclosure of dementia, but identifying other types of self-disclosure, for instance, detecting lung cancer users. Another thing that we consider that can be done is to evaluate the performance of our genetic algorithm with other types of large language models, such as Gemini, Meta AI, Qwen, ChatGPT, and so on. So in conclusion, we developed a genetic algorithm to optimize prompts for large language models to detect authentic dementia self-disclosure statements. We achieved an accuracy of 80% with the optimal prompt. And something that we thought was a bit interesting to report was that the self-predict mutation was the one that performed the best. Here's a list of the reference that we used. And please let me know if you have any questions. And thank you very much for your time and your attention.
We have time for 2 questions. Okay, Daniel, I have 1 question. So coming from how you define the question, it seems a little bit more like this is a prediction question, but this is a diagnostic question. However, when it comes down to dementia from a more healthcare perspective is a long-term thing, because you mentioned about adapting your method towards cardiovascular diseases or to lung problems, and those ones probably have a 5-year onset. Whereas for dementia is something that is very hard to detect because it might last for 40 years or more. So is there any way that you can change your model or reset up your model such that it goes from a diagnosis question to classify immediate people with dementia to a prognosis problem to people having dementia develop in the next 10 years?
So that's something that we haven't actually taken a look into. So far, the scope for our project was just basically because there's multiple studies that have used Twitter and X or other types of social media. And the way that they just basically defined their cohort was just to determine if the tweet or the post had the phrase, "I have dementia." They consider it as like a positive diagnosis. We ended up considering that that was not perhaps the most efficient approach to build cohorts. So we wanted to create something a bit more robust, basically, not just because it says I have dementia, it means that a person has dementia. We consider that as part of the limitation, as you mentioned, perhaps dementia might be something even more complex. But so far, this is what we've researched.
Okay, thank you. Any more questions?
Thank you for your talk. When you're using mutating new prompts, have you thought if there's any benefit of non-human readable prompts that still generate accurate responses? Because oh, sorry.
No, go ahead. Sorry.
That's if you have an answer to that part, that's fine. Go from there.
So that's a very interesting point that you bring across. Basically, something that we also aimed to do was provide some sort of like readability or explainability regarding how the model was doing its prediction, because we wanted to basically print out these results. Basically, the idea was that we wanted to create some sort of guidelines and to observe what the model was detecting in order to create some reasonable performance when labeling each of the users. So we did not decide to, or we did not explore some alternatives in which the instruction prompts that were generated were not like some human readable, because basically our intention was that someone could read these instruction prompts or like this sort of like instruction and interpret them as guidelines and see what type of things they might be missing or not taking into account when observing or trying to label the tweets. But definitely it's a very interesting new avenue, like perhaps just create some instruction prompts that are not human readable or not as readable as the ones that we are generating and see if the performance increases.
Okay, thank you, Daniel.
Thanks.
The next paper that we have is Which Side Are You On? Investigating Politico-Economic Bias in Nepali Language Models. This is a long paper and our presenter is online, Kritesh.
Can I share the screen? Hello.
Yes, you can share your screen.
Thank you. I guess my slides are visible.
Yep, we can see your slide.
Okay. Hello everyone. Today it's me Kritesh and I'm going to present our paper entitled Which Side Are You On? Investigating Political Economic Bias in Nepali Language Model. The highlighted are the authors of our paper. Coming to the first slide of which is introduction. As AI systems often reflect bias in their training data, which make it very crucial to evaluate and mitigate these biases, particularly in political bias, which have very skewed public perception and influenced belief. As AI become integral in area of news and digital assistance, understanding and addressing these biases is very vital and ensuring fair and balanced societal impact. Bias in large language model can influence application like new generation, potential enforcing political ideology and shaping public opinion. And ultimately, it can result in undermining democratic processes and trust in AI. While widely spoken language like English have received attention, biases in low resource language like Nepali remain unexplored. In this paper, we try to address the gap by investigating political and economic bias in Nepali language model, highlighting the societal impact. The main contribution of the paper are we manually translated political compass text from English to Nepali in order to access the political and social biases. We explored 5 Filmax model and 11 generative model for biases along the social and political axes. Our proposed methodology is well suited for evaluating bias in other low language model. Now coming to our methodology, this study employed two-step process to evaluate political bias in language model using political spectrum theory. This approach examines political opinion across two axes: social values, which has liberal to conservative like axes, and the economic bias, which lies from leftism to rightism. By integrating these dimensions, the methodology provide understanding of political tendency of LM, of obviously language model. To analyze these biases, we establish political encompass test. The PCT evaluate political opinion within the two-dimension framework based on the responses of 62 political statement. The highlighted are few example of questions out of 62 questions. Here, the opinion are from strongly disagree to strongly agree, and the user need to select one of those options. And for our study, we translated it to Nepali to English, and while translating, we used two native Nepali speaker, and the validation was carried out by three other Nepali speaker to maintain the accuracy. Both the Filmax model and generative model are used in the evaluation, providing the comprehensive assessment of biases in pretend Nepali language model. The dual axis analysis facilitate the deeper understanding of how LM reflects complex political ideology. Here are a few examples of translated PCT. On the left, on the second column, it is a English transcript which is provided by PCT, and on the right, this is a Nepali translation which are done by a Nepali speaker, native Nepali speaker. Similarly, the overview of our model evaluated are highlighted on the presentation. At first, for Filmax model, we used 5 Filmax model: Nevada, Nep News Bot, Nepali Bot, Debutter, and Distill Bot. These all are pre-trained on Nepali dataset. On the other side, we used generative model. We used two series, one of OpenAI series and one of Gemini series. And for open source model, we used 7 billion parameters, a part of Llama 3. We also employed 8 billion parameters model. And coming to our example of prompt, these are the prompt which we use during our experiment. The prompt is slightly different for Fieldmax model and generative model. On the below is the translation of the model, and this script is a Devanagari script. Nepali is written in Devanagari script. It has a different consonant and vowel, and the consonant and vowel are not constant. As the English language is, it changes while we change a few words during our speaking. Now coming to our results section, the research reveals the significant variation in political and social biases across Nepali language model. Smaller model which are trained on Nepali data set demonstrates similar economic bias, like the model like Nebata, NepNewsBird represent similar biases, score around 0.38 and also leaning slightly right, while the social score suggests that authoritarian tendency. Nebata and Debata scored the score of 2.41, while NepNewsBird score higher, about 4.72. Similarly, Nepali Bot scored 4.46. In contrast, large language model displays broader political position. Gemini Pro 1.5 and Gemini Flash 1.6 leans left of center economically, with score of minus 2.63 and minus 2.13, and it exhibits strong liberation tendency, especially for Flash 1.5 with a social score of minus 5.85. GPT-3 shows a moderate economic stance of 0.88 and the slight liberation score of minus 0.41, while GPT-4 and GPT-4o leans left economically and strongly liberation with a score of minus 1.44 and minus 5.03. One of the model of OpenAI's O1 preview and O1 mini model exhibit extreme left-wing economic bias and authoritarian social tendency. Among open model, Llama 2 and Mistral leans right economically, while Llama 3 and Gemma lean left. So socially, these models exhibit mild liberation tendency, with score ranging from minus 0.26 to minus 4.05. Notably, Mistral provide mixed language response, highlighting challenges in generating fully Nepali output. This finding underscored the diverse bias present in the model based on size, training dataset, and architecture. Also, we showed the graph representation of our score. The graph representation allow the user to easy reflection of what the language model were presented during our experiment. We can see that Nebata and other small language model leans toward authoritarian, and despite Gemini Pro leans toward the economic bias, leftism, and also show the libertarianism. Same goes to the other language model. This is the open source language model. We used only 4 open source language model, Lemma 2, Lemma 3, and the results are highlighted on the screen. Coming to conclusion, this study highlights significant ideology biases in Nepali language model influenced by model size, training, and data prior biases. Language models show greater biases ranging concern about their use in sensitive context. Addressing these biases is crucial for fostering ethical and equitable language technology. The finding emphasizes the need for detailed investigation into the case of biases and call for improvement in training methodology. Of course, all the research has few limitations. Same goes to this research also. The finding the finding on the biases in Nepali language model may not be generalized to all the other low resource language model due to its unique social and political context. The reliance of politic, political compass test limits the analysis score where there are various factors like gender, ethnicity, which is not presented in PCT, and this type of context can underscore the result overall result. Additionally, this study was constrained by the availability of smaller language model and limited data set, and we suggest that more language models should be built on the specific language and the data set should be more cohesive. Different like in Nepali language, there are not enough data set. The highly the latest model is Nebata, which is only trained on 10 GB data set, which is very low for the current research. And the research suggests that this can be overcome by utilizing more robust data. Mainly in data collection, research should be research should be done. This was from my side. If there is any question, please ask. You can ask.
Thank you. Are there any questions in the crowd? Okay, one question from me, Kritesh. If we go back into the comparisons, can you take, especially with the comparison on the metrics? Yes, this one, thank you. It seems like the smaller models and also the larger models have some differences, and this is very interesting to me. Have you ever tried to put individual instances into both the large model and small model and measure which one of these instances are giving the most disagreements in terms of the scores? And have you had a look into what causes a lot of these kind of misalignments?
We went coming to the open source model Mistral. It shows the responses was not accurate as it gave responses in English, but we already want in responses in Nepali. So we can say that in open source model like Mistral, it is mostly trained in other languages, not mostly in Nepali languages. So it gives a very complex result. And coming to our smaller model like Nebata, which are trained on Nepali dataset, as I said, these model are trained on very small dataset. It is trained in Nepali text, but it is very small. Those all the context related to the politics are not analyzed properly in those language model. So I suggest that in the internet there are various thoughts which people type in Nepali text nowadays. So building a LMs at the current year might solve this kind of errors, because because of the platform like Twitter and Threads, people try to present their ideology in Nepali script. So those script can be curated from the internet and it can be trained using Nepali model. And also people try to use some day-to-day conversation like in English. If you want to present I don't know, then people simply like IDK, so which is a very improper in while in professional communication. So this kind of nuisance data can be extracted and LLM can be robust for those type of general communication like general communication data set. Hello. Hello.
Oh, sorry, the mic was off.
Sorry, I'll
Okay.
repeat. Thank you for your presentation. My question was, how does these biases compare to English language biases? Like, is the Nepalese prompts biased in one way in particular? Are they more extreme, or are they more moderate, or do they fall very similar? Thanks.
Like in English language, there are various, like it has enormous data in English. So the biases like leftism and economic bias and the social bias are not that good, but it's them, but it is very better than the Nepali language. The obvious reason is about it is the English language is trained in very good data set, as uh, the global population use English as their like a professional language. So I think like in the Nepali language, it is not that accurate. The model gives either it gives extreme economic or extreme socialism. It few of the models only give them like a moderate result, but not all the models. Mainly for large language model, it's give either it gives extreme left or extreme right. It does not give that moderate.
Okay, thank you very much.
Thank you.
The next paper is called Lesser Shots, Higher the Hallucinations, Exploration of Genetic Information Extraction Using Generative Large Language Models. This is a long paper by Milindi.
Okay, cool. Let me just move here. Hi everyone. Good afternoon. I'm Milindi. What? I haven't muted. Sorry. Will I mute? Oh. Hello. All good? Yeah. Go. All right. Starting again. Hi everyone, I'm Milindi again. Today I'm going to be presenting our paper titled Lesser the Shots, Higher the Hallucinations, Exploration of Genetic Information Extraction Using Generative Large Language Models. First, a run through of what I will be talking about today. I'll be providing an overview of our research questions and the motivation for looking into extraction of genetic information from generative technologies. For context, for those of you who don't know, information extraction is a natural language processing task where structured knowledge from natural language text are extracted. This process was found to be pivotal for automating curation of biomedical information. I'll be discussing the experiments we conducted on genetic information extraction, the results gained, and the limitations observed. Finally, I will summarize our findings and outline the future directions of this research. Our main research question is on answering how effective general domain generative large language models are on the extraction of highly specialized genetic information from biomedical literature. Our primary focus was on the information extraction tasks of named entity recognition, where the entity spans are identified and annotated with a type, relation extraction, where the specified entities are identified and then the relationship between them is annotated and classified, and then end-to-end information extraction encompassing both named entity recognition and relation extraction steps. For context, generative large language models are a specific class of language models that generate content in response to a specific prompt. The output from these models depend directly on the structure of these prompts. The task of developing a suitable prompt for these models for a given task is called prompt engineering. Our research utilized 3 prompt engineering techniques. 1, varying the number of examples in the prompt. 2, providing an annotation guideline. And 3, providing an overview of the expected output structure to explore the effectiveness of these generative models. In addition to this, we actually embarked on the challenge of named entity recognition of genetic entities from Spanish language data, from Spanish language scientific text. We did this in the context of the Generative competition, which was part of the IBRLF 2024 campaign. Our motivation for this research was based on there being a need for organized genetic information for personalized healthcare and advancements of scientific discovery. Now, this is a simple overview of organizing genetic information. Here, the genetic entity spans are extracted from a given natural language text and annotated into the gene and disease types. Then the relationship between them is classified. The typical process of extracting such information is quite an arduous, time-consuming, and extremely manual process. With the exponential growth of literature, efforts have been made using natural language techniques to streamline and automate this process. And recently, methods based on generative AI has shown promising results for biomedical information extraction. According to our findings, information extraction has been conducted extensively across domains such as politics, literature, natural sciences, and so on, across various tasks. Researchers have mainly experimented with pre-trained, domain or task-specific large language models, which obviously were found to be much more performant than the general domain large language models. But using various prompt engineering techniques and various strategies to add more context, it was discovered that these general domain large language models actually show promising results. We also observed, in addition to this, that there is limited research on biomedical information extraction from non-English literature. This limitation was attributed to be due to lack of resources and because current large language models are predominantly trained on English language data. Lastly, prior work has shown that the complex nature of the language used in biomedical literature, paired with the exponential growth of literature, poses an ongoing challenge to develop robust models for genetic information extraction. Thus, we were able to find a gap in research that systematically evaluated the performance of general domain large language models on extraction of genetic information. This led us to specifically target entities related to disease-associated gene variation, including genes, mutations, and the diseases themselves. And utilizing prompt engineering techniques, we explored the most effective use of generative large language models across information extraction tasks. So, our experiments involved extracting genes, genomic variants, and associated diseases using 3 datasets. The first one being the annotated Spanish language dataset, which was provided for the Genovartis challenge. We used this to explore cross-linguistic and within language named entity recognition. Next, the TBGA dataset was used to explore simple gene-disease relation extraction. And then we used the Varium dataset to explore the extraction of complex genetic entities and the relations end-to-end. A manually crafted prompt library was created based on a template with variables that control the structure and the content of the individual prompts. These prompts contained fixed values for the instruction, annotation guideline, and the requested output structure for each of the information extraction tasks. In addition to this, we varied the number of examples from the training set that is embedded into these prompts. We used the generative large language model GPT 3.5 Turbo, as this model was shown to be quite effective for information extraction across various tasks. Lastly, we utilized BRAT-eval, a tool that performs pairwise comparison of entities and relations for evaluation of the extracted tuples against the gold standard data, getting the overall stats for precision, recall, and the F1 score. I forgot to mention, actually, during post-processing, we found the hallucinations and filtered them out and stored them for further analysis. So as I said before, the matched instances and the hallucinations are separated during post-processing. This is done by mapping each extracted entity to a position in the statement from the literature. All instances that were found in the text but could not be mapped to a position in the text, along with instances that were generated by the model that do not occur in the text at all, were filtered out as hallucinations from the model. The correctly mapped instances were then used for the evaluation. Each of the individual prompts were created adhering to a specific learning paradigm, such as zero-shot or few-shot, which is providing either no examples or a small number of examples of the solution to the task in the prompt itself, guiding the generative large language model to the desired output. Additionally, the impact of providing more context to the model was explored with the addition of an annotation guideline and an overview of the output structure. The prompt shown here includes an annotation guideline, the overview of the output structure with one example from the training dataset. Based on our experiments, the best performance was seen with few-shot prompting for Generative and Variome datasets. Learning paradigms seem to have had very minimal effect on identifying relations using the TBGA dataset. It can be seen across all of these three information extraction tasks that recall is actually higher than precision for few-shot prompting. This shows that a significant amount of correct instances were extracted, even though there were false positives. The opposite is obviously observed for zero-shot prompting. We also noticed that with the increase in examples in the prompt, more variations in the entity types extracted and the relations were identified. For example, as shown here, entity types cohort patient and body part and the relation types biomarker being extracted more with the increase of the examples in the prompts. During the analysis of the discarded hallucinated instances, two types of hallucinations were observed, namely overgenerated hallucinations and fabricated hallucinations. Overgenerated hallucinations were instances containing one or more entities that were found in the accompanied text which could not be mapped to any position on the text after all the previous occurrences of that specific entity has already been mapped. Fabricated instances included entities that were not found in the text at all. We observed a steep decrease in hallucinations with the increase in the number of examples across tasks. Hallucinations for the TBGA dataset were mainly fabricated instances, while Generative and Variome consisted mainly of overgenerated instances. In a nutshell, addition of examples in the prompts lead to increased performance across tasks for genetic information extraction. This can be attributed to the model's ability to learn in context. The model performed the worst for the Variome dataset. This can be attributed to the complexity of the domain-specific entities and the relations in the dataset, plus inadequacies of the prompt structure. Additionally, the best performance for extracting entities from Spanish literature was seen using an English language prompt. This was attributed to the large language models being predominantly trained on English language data. One of the key failures that we observed was the inability of the model to adhere to the task outlined in the prompt, leading to the hallucinations and incorrect extraction of entities and relations. These hallucinations can be attributed to be due to various factors, such as the complexity of the information extraction tasks, limitations in the prompts, the generative nature of the model used, and the model not being specifically trained on genetic data. Lastly, a high amount of false positives were observed as the extracted entities were exact matched against the gold standard data. In conclusion, Our paper explored the use of a generative large language model for genetic information extraction across several tasks and data sets, utilizing various prompting strategies built upon best practices in relevant literature. Through our evaluation of prompting strategies, we have shown that few-shot prompting provides optimal performance for tasks involving named entity recognition, and that learning paradigms have a minimal effect on identifying relations. Key limitations of the generative model include overgeneration and fabrication of entities, showing that generative models struggle to adhere to the tasks specified in the instructions. We have discovered that increasing the number of examples in the prompt, the addition of an annotation guideline, and specifying the overview of the output structure not only improved performance, but also reduced the overgenerated and the fabricated instances observed. Unfortunately, due to the limited time frame of this research, we were unable to gain access to other models. Plus, due to lack of publicly available data sets, we were unable to experiment with additional data sets which were task-specific with complex genetic entities and relations. Because comparisons between more models and more of these data sets could have had the potential to provide more information and credibility to our experiments. In conclusion, further research needs to be conducted to explore ways in which performance can be optimized, along with minimizing the negative effects of using generative models for information extraction in the biomedical space before using them practically. Thank you very much. Any questions?
Hi, thank you for your talk. I'm just wondering, so maybe I missed it, but do you have comparison between your models and the baselines on these 3 data sets?
Sorry, so we only use the GPT model only. We didn't compare with any other models or any baseline.
I mean, in the existing literature.
Sorry.
In the existing. No. I see. But like, have you come across anything? Because then that would give like a good idea, right? In terms of like whether like LM is a good approach to NER in this space. So it's
yeah. So basically, there exists literature that has like compared the general domain and the trained ones before, which showed that the trained ones obviously give the better performance. But for our experiments, we only just used GPT 3.5 and kind of looked at the various tasks and the performance of the model.
Hi, thank you for the amazing talk. My question is that like those entities in this gene task, they could have indirect relationship, right? So for example, there are 3 genes, for example, A, B, C. A might have an impact on B, which then impacts C. So have you experimented with the impacts of field shots on such relationship types?
I don't think we did actually experiment with like the transitive property of the impact of the relations. We mainly wanted to see if the GPT models could extract that information that is already presented in the literature itself, so that we could have like this gene results for just this disease and then this other gene for this disease, but there is no correlation between those 2 genes. Thank you for your question. Oh, thanks.
Okay, and the next paper, the last paper of the session, Simultaneous Machine Translation with Large Language Models by Minghan Wang online. And this is a long paper.
Okay, thank you. Let me share my screen. All right. Okay, so I'm Minghan Wang, and I'm a PhD student in Monash University, supervised by Reza, Aisan, and Chuang. And thank you for having me to present my paper. The title is Simultaneous Machine Translation with Large Language Models. So let's first talk about some kind of a background about simultaneous machine translation. So basically, simultaneous machine translation is used in various applications. For example, live conference interpretation, live subtitling, or cross-lingual communications. And it is actually very different from offline translation. And the offline translation is referred to some applications such as, for example, Google Translation, or also if you use, for example, ChatGPT to translate some kind of documents, they are all belongs to offline translation. And the goal of offline translation and the simultaneous translation are very different. For offline translation, it pursues more on the translation quality, but for simultaneous translation, it also has strict requirements on the latency. So this will lead to a very different thing about the context utilization. For offline translation, it can use the full context, but for simultaneous translation, it can only use partial context. In terms of modalities, both of them support, for example, there are many researches on both of them, including the text-to-text, speech-to-text, and speech-to-speech translation. And here is a detailed example of the difference between offline translation and the simultaneous translation. For example, for offline translation, the translator will have to wait until the speaker have finished their words and then start the translation. So it will use all of the context. And for simultaneous translation, the goal is to reduce the latency. So it will need to start the translation together with the speaker who is speaking now. So it will it can only use the partial context. So simultaneous machine translation is often modeled as an MDP problem with two types of actions, including the read action, which means read in more source context. For example, in this figure, in this blue arrow, it reads some new tokens from the source stream. And the write action actually is to write out the translated tokens, for example, here. And although this kind of simultaneous translation seems to be running in parallel for the input and output stream, but essentially it works in a sequential manner like this. So for this problem, there should be a policy that is applied to coordinate this process. The policy can be a conservative policy, for example, read as much context as possible, so that it will lead to higher quality, but also higher latency. And you can also use an aggressive policy, for example, to write as quick as possible, and this will lead to lower quality, but also lower latency. And there are actually a lot of approaches has been proposed to obtain a balanced policy. For example, some of them are fixed policy, and the most famous one is the top K policy, and there are also some adaptive policies. Some of them are learned policy. For example, you need to design a specialized loss function or architectures and train the model to learn that policy, such as this monotonic attention and weight info policy, or there can be heuristic policies, such as this incremental decoding policy. And this one is actually used in our paper. And why we are using RM for simultaneous translation? As we know that there has been a lot of work showing that RMs are good at offline translations. For example, they can handle culture-related context, and they are good at document-level translation due to their long context window, and they are able to perform flexible style adaptation and has strong cross-lingual transfer capabilities and are robust to noisy input. So we are expecting that all of these kind of properties can be transferred to the RM when applied on the simultaneous machine translation task. But actually, you find that adapting RM to simultaneous machine translation itself is very challenging. From the architecture aspects, we found that decoder-only architecture is not built naturally for incremental translation. And the standard RM decoding algorithm doesn't really support simultaneous encoding and decoding because basically in conventional studies, most of this simultaneous MT model uses separated encoder and decoder. And in terms of policy design, we may need to design a specialized read-write policy, and we'll have to adapt this policy to LLM through, for example, fine-tuning. So basically, our goal is to enable efficient LLM-based simultaneous translation through novel solutions. So then we find that this incremental decoding algorithm is actually a very good choice to do so. And this algorithm is actually proposed in some previous studies and was originally used to convert a standard encoder-decoder MT transformer model to a simple MT task. So basically, in our study, we extended it to support decoder-only architectures and also optimize the decoding latency. So let me introduce the details of how we are doing it. So basically, in this incremental decoding algorithm, it runs in a round manner. So in each round, it basically reads something in, for example, reads some source context in, and it can choose to write out some translations. And basically, it involves 5 steps. The first step is that it reads a trunk of source context, and the size of this trunk can be fixed or adaptive. And after reading these source tokens into the buffer, we can put that into the prompt, for example, translate something to German, and then put that into the LLM generated with the beam search algorithm, and then we can have a list of beam candidates. And at this moment, we will be able to gather some kind of a most confident prefix and use them as the translated tokens to write out. And here is a specialized module to perform this kind of a selection. And originally, this module was actually the LCP algorithm, which is the longest common prefix algorithm. And during the experiment, we found that that algorithm has a very negative effect on the latency. So we made some adjustments on that. Okay, so basically, yeah, let's have a look on this LCP algorithm. So in the original LCP algorithm, if the first token doesn't have any kind of agreement, then the model will need to give up this chance to write out anything, and it will need to read another trunk of source tokens. And eventually, this will significantly affect the inference latency. So in our paper, we propose to relax the criteria of this kind of a prefix selection by introducing a type of voting mechanism, so that, for example, if 60% of tokens have the agreement, then we can choose this trajectory as a prefix. Okay, so let me introduce our experimental setup here. So basically, we use the we use a commonly used data set, which is a must-see data set, and it contains 9 language pairs, all from English to other. And we also generated a small proportion of prefix to prefix data set using the GPT 3.5 model, but we found that this part of data set doesn't really helpful. And in terms of the baseline model, we use the vanilla transformer model trained on the must-see dataset and decoding with the incremental decoding algorithm. And for the metrics, we use BLUE to measure the quality and the LAL for latency. And there's one thing you need to mention, that this LAL is not a latency measurement matrix that involves the computational latency. It only measures for example, the distance between the translation and the speaker, which measures like the lagging between them. And in terms of the LLM, we basically use the Llama 2 7 billion chat version, and we have tested both of the original instruction tuned version using the one-shot prompt, and also we tuned the model on the must-see and the prefix to prefix data. using the LoRa SFT for 1 epoch of training. And in terms of the inference, we tested both of the offline translation and the simultaneous translation. So here is the overall results. And we basically have 5 groups of results. The first one is the offline baselines, which we directly use the transform model to translate in offline mode. And the next is about the offline translation using RMs, including using the one-shot version and the SFT tuned version. And then it's about the simultaneous baseline using the transform model. And this row with the star here is the version that uses the RALCP proposed in this paper to reduce the latency. And the next group is about the simultaneous translation version using the one-shot RM, and the last one is using the tuned RM. So we found that one-shot results are actually not good, but it's strongly correlated to the language coverage in the pre-training corpus, because as we can see that in this, we made this statistic by gathering all of these kind of values from the Llama 2 paper, and found that the coverage of all these languages are actually very small. So it is actually within our expectation that the performance is not good. And we found that RALCP algorithm is actually very effective to use to reduce the latency, and it is particularly powerful when applied on ARMs compared to applied on the original transformer model. As you can see, if you compare this red value to the original non-RCP version, the reduction is very significant. And we found that after SFT, RM is very competitive if you compare this blue value to the, for example, transformer baseline here. Yeah. And except from the overall result, we also conducted some analysis. The first one is about the investigation of the data utilization efficiency for RMs. So basically, we selected 3 languages that covers that has different language coverage in the pre-training corpus, including the German, Russian, and the Romanian. So basically, we found that thousands of samples are enough for RM to obtain good performance. So it is actually very efficient. So as you can see that basically when using like 10,000 of samples, it is enough to mitigate this kind of language coverage difference in that. And another analysis is about to investigate whether the model has some certain resistance of noisy inputs. So we use Whisper to generate the ASR transcripts using the must-see test set, because the original must-see data set was actually used for speech translation. So we use that for so we use the Whisper to generate the transcripts and compare with the ground truth inputs. And actually, we find that RM doesn't really show significant advantages, and we guess that it might be due to the over optimization of SFT, since we use all of the training samples in the must-see dataset. So basically, the RM may have already lose the capability of this. And the last one is about the computational overhead. So we basically recorded the time per token when the time per token during the inference for the baseline transform model and the RM. And as you can see that RM has a very higher value in terms of this metrics, and it indicates that RM has a significant higher computational latency, and this becomes a limitation for practical application. So basically, in conclusion, we explore the possibility of using RM for simultaneous translation task, and we propose to use the incremental decoding and extend it to the decoder-only architecture, and we optimize the prefix selection algorithm, which is the RALCP, to reduce the latency. And through the experiments, we found that the proposed algorithm can actually conveniently convert ARM into a SimulMT model, but the performance is actually limited by its intrinsic multilinguality. And we found that using the offline translation corpus to tune the ARM could easily obtain competitive performance, and it has good data utilization efficiency, but didn't meet our expectation on the robustness of input, noisy input. And a noticeable limitation is the computational cost of ARM, hindering the practical application of it for the simultaneous translation task. So in our future work, we will try to address this kind of a computational cost problem and reduce the computational latency. Okay, so I think that's all of it. Thank you so much. So any questions?
One question from my side. So thank you for the presentation. I'd like to know that how do you actually compute the LAAL? What is the actual way for computing it?
Okay, yeah, sorry, I didn't include the detail of that matrix here. So basically, LAAL is something like you measure how many tokens. Basically, it's something like how many tokens the translation model that is lagging behind from the input stream, something like that. But the actual formula is much more complicated than that. Yeah.
Okay, cool. And the reason why I asked for it is because from the experimental results where you show with the table and also with the brackets, yes, we can see that the LAL, which is the lower the better, the results are much better than when your method, so LCP, is actually used. So I'm wondering whether or not is it because the normal CP method actually just drops off some of the tokens basically were not used because it cannot maintain in the beam search. Is that the reason why that your results are much better?
Sorry, I didn't get clearly about your question. So can I repeat?
Yeah, no problem. So over here we can see in the red, so the LAL, your results are much better than when RAL-CP is not being used. And if you can go back about 2 slides, yep,
here.
if we take a look at, not this one, but the other one where it shows the difference, yep, this one over here.
Okay.
In the normal LCP method, it shows that they'll always try to keep the first token, but if later on it's not being used, they'll drop it. And I'm wondering that whether or not the LAAL method is actually getting a better result because it's not dropping off all of these unused tokens.
Well, actually, I don't think so, because eventually we have also measured about the final length of the translation result, and actually the length of the translation doesn't really have a much difference between them. So yeah, I guess it doesn't really affect because of that. Yeah.
Okay, cool. So it's just latency is much better with this method that you're proposing.
Yeah, because when using this RLCP, it can actually I mean, using any chance to produce the result, but not wait longer. Yeah.
Okay, thank you.
Okay.
Oh, hello.
Hello.
Yes. Hi. Yeah. Thank you very much for the presentation. I don't have a question, but it's more a terminological feedback. So I'm Jordy from the University of Melbourne, but I'm also like I have NATI certification in interpreting and translation. So what you're calling simultaneous machine translation is actually simultaneous machine interpreting. If you use the language of interpreters and translators, so an interpreter is somebody who takes like basically spoken or speech from language A into language B and back. A translator is someone who takes written text from language A to language B and back. And Oh, well, there's another variant where you take a written text and then you interpret orally. So just thought I'd flag this. It's probably not much of concern for like computer scientists, but just because when talking to interpreters and translators, one thing like you hear people like people who not from that profession, they don't understand the difference between an interpreter and a translator. Yeah, just thought I'd raise that here. Thank you.
Thank you. Yeah. I think that is a good point, because basically I found that also in this kind of a simultaneous translation domain, most of the research doesn't really distinguish about that. Yeah.
Okay. Thank you.
Thank you. Yeah. All right. So thank you so much.
Okay, so that concludes this session, and now we're going to afternoon tea, and afterwards we'll talk about the share task. Thank you.